Okay, welcome everybody. So far we've discussed what the null space for an m by n matrix would be. In this video, I want to define what the column space of an m by n matrix is and take a look at an example. So the column space of an m by n matrix A. So if A is m by n is the number of columns. So I'm going to denote each of the column vectors of matrix A with a bold A with a subscript, and we've got n of them. And note that each of these column vectors is an element of Rm, since we have m rows in this matrix. So first of all, we denote the column space with column COLA, and it's the set of all linear combinations of the columns of A. So we can write that as the span of the column vectors of matrix A. And another way to think about this would be it's the set of all vectors B in the codomain of this matrix. So we're thinking about where the vectors get mapped to, such that there exists some x in the domain so that when we apply matrix A to vector x, we are able to map to this vector B in the codomain of the map. So let's take a look at an example using the same matrix A from the previous video. So here A is a 2 by 5 matrix. The top row is 3, 6, 6, 3, and 9. And the second row is 6, 12, 13, 0, and 3. And we want to find the column space of A. Well, here's a really obvious answer where I can just write the column space of A is the set spanned by the 5 different column vectors of matrix A. But what might be nice, and we're kind of leading into a little bit of material that we'll get into when we discuss bases and things like this, is do I need all of these vectors listed in this set? So I can see, for example, that these first two vectors, one is a scalar multiple of the other. So the vector 3, 6 and the vector 6, 12, it's just 2 times the vector 3, 6. So by eliminating this second vector in this set, this does not affect the number of vectors that we can get by taking linear combinations of the other 4 vectors. So I'm going to cross off this vector 6, 12 because I can see it's kind of redundant with this first vector that we have. This vector 6, 13 is not a scalar multiple of the first one. So by taking linear combinations of 3, 6 and 6, 13, we can get some additional vectors back. And the question is, well, do I need all of these vectors to write out the column space for matrix A? And we don't. We've already seen that this is a duplicate over here. And so what about the next vector 3, 0? Well, we can take a linear combination of the vector 3, 6 and the vector 6, 13. We can take a linear combination of these two vectors and generate the vector 3, 0. So if I exclude this vector from my set, we're not changing the amount of vectors that we can get in this by taking linear combinations of these sets of vectors. And similarly, we can show that this last vector 9, 3, it's a linear combination of 3, 6, and 6, 13. I can take 33 times 3, 6 minus 15 times the vector 6, 13, and that gives me 9, 3. And if you're curious where I found this information, I put a link to a Google Colab notebook where I did these calculations in the description of this video if you want to check my work. So this means that we could also remove the vector 9, 3 from this list of vectors, and the column space of A we can write more succinctly as the set spanned by the vector 3, 6 and the vector 6, 13, and the additional vectors are already linear combinations of these two vectors. So this is all we would need to list to get the entire column space from matrix A. And I just want to connect this back to the result that we saw when we were finding the null space for matrix A. We took that original matrix A over here and we wrote it in reduced row echelon form. And again, the details of this you can do using Python in the Google Colab notebook linked below. And this matrix in its reduced row echelon form had two pivots. Column 1 and column 3 were the two pivot columns. And notice that if I pick the original two column vectors associated to the pivots, these are the only two vectors that we need to form the column space of matrix A. So there is some connection between this reduced row echelon form and how we can represent the null space of matrix A and how we can represent the column space of matrix A. And we're going to revisit this in more detail.